So good morning. I have one good news for you, and that is that this is the last lecture in the course. We've made it. It was easy, right? I mean, probably the most difficult thing was waking up early in the morning, as evident by the influx of people. I hope that a lot more of you show up after the break so that we can have the course evaluation. The forms are over there. Well, let me fix the resolution again. Oh, and now I understand what the problem was. Oh, God. Just doesn't want to. Keep it. Okay. Finally. So the forms over there, we'll do it after the break. I ask you to take them during the break, so take them at your desks during the break, and the first 15 minutes of the second part will be spent on the course evaluations. I am obliged to say that the course evaluations are not so much about the lecture itself, but more about the lecturer. So most of the questions will be evaluating the lecturer. So if you think that the course, if you have an opinion about the course material, that is, the course is boring or not interesting or it could be improved and so on, you can write this down in the manual feedback section. But don't expect that you get questions evaluating the course concept. This is evaluated in a different way. All right. So today's lecture continues kind of what we started last time, and that is the business cycles, modeling business cycles. Basically, this is the same slide as last lecture. A quick reminder, what we looked at so far was kind of a mathematical way to get oscillations, right? We looked at basically the nonlinear dynamics. We have a dynamical system. We didn't specify exactly what dynamical system that is. Could be everything. We looked at factory, supply chain, for instance, and then we simply took control parameters and we saw how the dynamics of the system changes qualitatively in terms of bifurcations by varying the control parameters. But there was still kind of something left out, and that was more of a real application of these concepts in terms of economics. So that's basically the last two lectures, the last three lectures actually, looking at oscillations, looking at the economy as a dynamical system. And this is not something new. Economists have been trying to do this precisely to address criticism for the equilibrium assumption that neoclassical economics has, and that is economy is always in equilibrium, and all we can study actually is how the equilibrium changes if we change some fundamentals, right? Obviously, this is not a satisfactory explanation of the real world, and that's why people started modeling business cycles. But I have to say that the economists who try to model business cycles, most of them, I would not like to say all of them because I'm not an economist, so I don't know, I don't have all the information, but most of the economists are not neoclassical economists, right? So you will not find proponents of free markets, of efficient market hypothesis. You will not find an economist like Eugene Fama, for instance, studying business cycles, right? Because for neoclassical economics, there is no problem. If we're in a recession, for instance, there is not enough supply, there is not enough demand for labor, then what will happen is the wages will go down, and eventually it will become profitable for employers to hire again. And then the economy will bounce back. So there is no problem for neoclassical economists to explain recessions and business cycles, but it's still not satisfactory. So all these economists, starting actually quite a long time ago, 1938, they've been trying to kind of depart from this classical view, and that's why we emphasize here. This is not an economics course, but I just like to give you some kind of economics foundation for doing this. It's not just because we like to have some mathematical equation and call this variable supply and this variable demand. Last lecture, I introduced the Caldor trade cycle. It's one of the most famous business cycle models. I saved the economics behind it. It's written nicely in Caldor's paper. Now I'm thinking that it may be a good idea to introduce the economics. So I will probably, introduce it briefly. So I will probably do it next week at the summary lecture. I will introduce this quickly, these nonlinear functions, investments and savings functions, and explaining kind of the economic rationale behind the slopes and the shapes. Basically, it would be a summary of the Caldor's paper. It won't be new to you if you've read the paper. Today, we continue with more business cycle models. And these are the models, with the exception of, now I cannot use this tool, so let me try to open the lecture in another way. Okay. Now I can do this right. These are the models we're going to be studying about, we're going to be talking about, with the exception of the second one. It's just we don't have enough time. So all the others we're going to address, with the exception of the second one. So the first one, how many of you have heard the name Keynes, the economist? The economist. Oh, wow, nice. So you probably know his his economic idea, which is not as what popular opinion holds, that he's a socialist or communist. He's actually trying to fix capitalism. So his main concept is that through fiscal politics, so government spending, public spending, you can fight recessions, right? So if there is a recession and there is not enough private investment, so firms don't want to invest, don't want to hire, then it's the government who can step in. And I always think about all the construction work going around Zurich all the time. Although to me they sound like perfectly, they seem like perfectly good streets, but they're still being reconstructed. So it could be, and probably it is, some kind of Keynes concept there. But this is his main idea. The government, through fiscal politics, can fight recession. Obviously, this is at odds with the standard markets are most efficient, all this kind of stuff. Well, Keynes was criticized a lot, especially by Milton Friedman. He's another famous economist, proponent of the efficient market hypothesis and so on, but that's irrelevant. The point is that all these models, if you want to model business cycles, you kind of assume Keynes' position. So all these models are just mathematical representations in one way or another of his ideas, because actually he didn't leave any formal mathematical description of his ideas. So people are trying to formalize them. Of course, adding a little bit here and a little bit there. The first one is Samuelson. It's a very interesting model, very simple, in fact. That's why it's interesting. So he simply assumes that consumers always consume a fraction of their income. This is called the multiplier concept. So you multiply kind of the income by a fraction, and this is what you consume at each time step. Investors, they invest a fraction of the increase of consumption, right? So if consumption increases by, let's say, 1,000 arbitrary units, the increase, or the differential in consumption, then investors would invest a fraction of this, not a fraction, but a multiple of this. It could be larger than 1, and this is called the accelerator. We'll see this in details. So the second model is, well, just to give you an idea, the assumption here is that the economy grows trend-like, so there's a trend-like growth, but oscillation, you don't see this trend in the short term. You only see oscillations around the trend. So the economy grows basically like this. John Hicks, it's an improvement of Samuelson model. We'll see what improvement exactly, and then when you look back in this slide in retrospect, you will understand what this means. And the Goodwin model is different from all these other models because it explains business cycles endogenously. Probably you're all familiar with exogenous versus endogenous. Only with the Goodwin model we can get business cycles that are produced by the internal dynamics of the system, not imposed by some external parameter. We're going to see this. So Paul Samuelson, I tried to, by the way, I forgot to say, this is a brand new lecture. So it was never given in the years before. These are kind of infant slides. And yesterday I was going through them again, and I found a lot of typos. So depending on when you downloaded the slides and printed them out, you may have a slightly different version. So to be safe, just download them again. They would be the correct ones. If you've downloaded them in the morning and printed them out just now, then you're fine. All right. I tried to give you a little bit of information about each economist. So for instance, Paul Samuelson was already at university at the age of 16. You can read this at your leisure. He's the author of the best-selling economics textbook of all time. So that has to count for something. All right, let's get right into the model. By the way, I forgot the other presenter, so I'll try to keep track of time with my cell phone. All right, so Keynes was originally suggested the idea of the multiplier, and the multiplier is simply this. This is the multiplier. For historical reasons, a parameter like alpha was, came to be called the multiplier, although it's just a fraction. I would call it a fraction, but nevertheless. So the idea is that consumers are backward looking. So they see what their income was in the previous time step, or last year, and they consume, and currently they consume a fraction of it. All right? And this is the multiplier effect. This is the original suggestion by Keynes. Now Samuelson came, and he introduced also the idea of the accelerator. So another, for me, it's again just a parameter beta, which could be called a fraction, but for historical reasons, it's called accelerator. So we have the multiplier here. This is consumption. And the investment now is consists of two parts, and you can recognize Keynes' touch here. So investment consists of autonomous part, which is always there. You can think of this as government spending, constant government spending at each time period. So it does not depend on the economic condition at the moment. It's always there. This is the autonomous part, and we assume it's a constant at each time period. And the induced investment. So the induced investment, this is the IT and superscript IND. This is what private investment is. So you induce capitalists to invest. And how are they induced? They're induced via the accelerator concept, this one here. So they see how much consumption or demand has increased over one time period, and they invest in production in order to satisfy this increase, right? So they're not really extrapolating or doing some fancy statistics on the demand, right? They just look at the most recent demand increase right? So if that is positive, then they will have to invest more in production in order to satisfy this expected demand. So that's the idea, accelerator and multiplier, and you can see how the two interplay. So if the government jump-starts the process by investing something, and actually it's the next slide, but I'll explain it now. By investing something, consumption would increase, right? From zero, suddenly we have an output generated entirely by the government investing. This is the autonomous part. Consumption, positive consumption would increase due to the multiplier. Then the increase in consumption would be kind of modulated via the accelerator and induce investment actually. Induced investment would increase the output. Increasing the output increases consumption, and this increases the differential here. Investment increases again, output increases again, consumption increases again, and so on, and you can probably see where I'm going. It's an explosion. Right? And we'll see that this is in fact what can happen, what in fact happens. And yeah, so this bullet point basically explains this interplay. Samuelson just made a simple calculation, so he did not go through computer simulations, bifurcation diagrams. He just made this simple table. So here we have the current government expenditure. Well, that is the autonomous part. Right? So here is the assumption that the government is providing at each time step something. So in the beginning, there is no consumption because there is no output. There is no investment because there is no differential in consumption. The only thing that can happen is the government jump-starts the process by investing, I think this is dollars. Yes, by investing $1. It could be a bit confusing, but this is a 1. It's not a capital I. So investing $1, the total outcome of the total output would simply be $1, right? Remember, the output is equal to consumption plus investment. Consumption is 0. Investment is simply the government investment here. So that's $1. So output is $1. Yeah, so I forgot to say that alpha is 0.5. So consumers consume half of their income, and investors, they simply take the accelerator to be 1. In the next time period, consumers would see, oh, we had $1 of aggregate income, so this is aggregate income. Let's consume half of it. We consume half of it. There is now a differential in consumption of 0.5. Therefore, the induced investment would be 0.5. The government still keeps investing $1. Therefore, the total outcome of the economy or output of the economy would be $2. And in the same way, you can go on and you see what happens to the total outcome. It grows, and then it starts to decline, and then it starts growing again, starts declining again. So you can probably already spot that given these parameters of alpha and beta, we get kind of a cyclic behavior. In fact, this is not a cyclic behavior, these are damped oscillations. We'll see a phase plot later on. But this model can produce cyclic behavior at a very, very limited parameter range, which is one of its deficiencies. So you're probably wondering, what does this mean, minus 0.125? So this is induced investment is negative. Right? This simply means that the investors or capitalists, they do not invest at all. They just simply let things depreciate. So that's why, in a sense, some part of the capital good is lost because it gets depreciated and it's not covered by induced investment. It is covered, though, by government investment, right? That's why the total investment can never be less than 0. Okay. So this is a very simple description of the model. Let's look at how it behaves in a more systematic way. As I said, the output of the economy is just equal to consumption plus investment. We can rewrite the investment in the following way: autonomous part, or government, or kind of public spending, plus induced private investment. And by expressing the output in terms of alpha and beta, we get that here. And we can substitute the consumption. Remember, the consumption is equal to alpha times the output in the previous time step. So we can substitute this one, and this one, and we get a second order difference equation for the output. It's a non-homogeneous equation because of this term. Anyway, in the notes I've given you the solution. We solve this equation exactly in the same way as I've shown you in the previous lectures. We had different equations and they're solved in exactly the same way, but here I've given you just in the notes the overall form of the solution, namely the x1. If you look, x1 and x2 are just given as the roots of this polynomial, because if I have to write them down, they would be very messy expressions. And this will simply confuse us. But if you just look at it, you can immediately see that if x1 and x2 are both negative, we get what? It's in the notes. If x1 and x2 are negative, what do we get? Do we get explosion? No. We get damped oscillations to the equilibrium value. Conversely, if they're positive, we get explosions. So only when they're kind of the interplay between x1 and x2 is balances somehow, balance them out, then you can get oscillations. But we'll see that this is in a very limited range. All right, so this is the equation. The stationary state is given by y bar. And you can calculate the stationary state easily by setting yt equal to yt minus 1 equal to yt minus 2. Right? This is what stationary state means. Given the stationary state, we just compute the consumption, the steady state or stationary consumption, which is just the multiplier, alpha times the stationary output, and the investment now. Yes?
Sorry, in previous slide.
Yeah.
Net national product. How do you find epsilon t equal alpha c t minus 1?
Alpha ct minus 1. Oh, yeah. So there's another typo. So this should not be C, but it should be Y. Okay? It's simply, what we're simply doing is consumption plus investment. Consumption should be alpha times yt minus 1. And then this is the investment. Good, thank you. I'm impressed you were able to follow so fast. Yes, so, right, this is Y. Good, and now, why, so we see that this is the stationary state of the output. We can calculate the stationary state of consumption. Now, why would the stationary state of the investment, or long-term investment, why would it be equal only to the autonomous investment, only to the government spending? Where is the induced part? We had an induced part, but now it's gone. So in the long term, there's no private investment. Why is that the case in this model? Let me just show you the equation. This is the equation for the total investment. It's the sum of autonomous plus induced, and suddenly the long-term investment is autonomous. Yes? Yes.
That implies that I piece or difference is constant.
Yes. That's true. So it's precisely this. There is no differential anymore in consumption because we have a stationary consumption. Makes sense. And it can also be shown that this stable point, or this stationary point, is stable only if alpha is smaller than 1 over beta. More interesting is the phase plane, right? And this is in fact, so the phase plane, this figure without these things is taken from the paper of Samuelson, from Samuelson's paper. And these kind of phase plots I added manually. So basically, when you simulate the model, you can create these phase plots. Unfortunately, you can't see the axis. This is simply a phase plot. So on the x-axis here, you have y of t, the output at time t. On the y-axis, you have the output at time t minus 1. Right? So this is the two most recent outputs. And what you can see is the following. Now, on the y-axis of the large plot, we have alpha. This is the part that consumers consume, the part of the output that consumers consume. Obviously, it can never be larger than 1. So if you look carefully, there's like a bold black line at 1. Consumers cannot consume more than what's available physically. Beta, on the other hand, can go basically in any range. So in a sense, this is kind of the reaction of investors. If beta is very high, they really overreact to any differential, any small differential. If it's small, they're not sensitive at all. So what we see is the following. By the way, I've tried to do it to put the plots in the regions where they belong. For instance, in the region B is basically everything below these curves. This is region B. The dynamics looks like this. At region C, which is simply the space, the area between these two curves, is this one. Region D is the area between the horizontal line at 1 and this. And now region A is just this little thing here. This little area. But I couldn't put this plot here, so have in mind that this plot refers to region A. It's not that this plot refers to values of alpha which are bigger than 1, which obviously doesn't make sense. So what we see, and what you cannot see, unfortunately, these little arrows, I hope you can see them, but this arrow, and yes, so this arrow and this arrow, they point downward. So the dynamic starts from here, and it finishes here. Here, the dynamic starts from here and ends up here. This one starts from here and explodes. No, sorry. This one starts from here and again goes to a stable state, like that. And this one simply increases all the time. So the arrow points upright. So basically what you can see is that for most of the parameter ranges, if not, for most of them, you either get damped oscillations like region A, B, and C, or exploding oscillations, which is region D. That's the only thing you get. Only when alpha equals 1 over beta, which is that line, this line here, basically this one, this line. So this is when alpha is equal to 1 over beta. Only then do you get oscillations. And I've put the plot there. You can see there are oscillations there. So it's kind of a business cycle model, but it produces business cycles as kind of an exception, right? In most cases, it either explodes or dies down. And that motivates a lot of the critical points on this slide. So, namely the third bullet point. Business cycles are only a boundary case. But moreover, the cycles have a fixed duration and fixed amplitude. You can show that, which is obviously again not realistic. Real economic cycles, you can claim they more or less have an average period of, I don't know, 4 or 5 years, but it's by no means fixed, or the amplitude is by no means fixed. Yet in this model they are. The marginal, so the beta, if you think about the, if you think about the alpha again, let's go back just to show you. Right, if you think about the alpha again, you can interpret alpha also as the marginal propensity to consume, right? If you differentiate this thing with respect to consumption, then you get the marginal propensity to consume is alpha. Yeah. So 1 unit of output induces alpha times this units of consumption. It's constant in the model, right? Alpha is constant, but of course this is not, again, really realistic. We know that, actually it's been shown that as people become more wealthy and wealthy, their consumption kind of saturates at some point. There's only so much they can physically consume. So alpha is by no means constant in the real economy. Yes, so everything else I said. And I've said here that as a response, the nonlinear Higgs model was developed. Now, why is it nonlinear? Or in other words, why is this model linear? If you look at the equation for the yt, so yt equal as a function of yt minus 1 and yt minus 2, you would see that it has linear coefficients, so it's a linear model. Therefore, John Higgs developed a nonlinear model, which is an extension of this one, and he tried to address these critical points. Some of them, not all. You'll see that some of these points still remain in the Higgs model. So this is John Higgs. In fact, I should have said Sir John Higgs because he was knighted in his lifetime. But this is the model. So his idea was very simple. He said, well, I mean, it's kind of a first order solution if you'd like to think about it in this way. He saw that the Samuelson model produces explosions or complete kind of convergence to zero or to the autonomous investment. So he said, well, let's introduce upper bound and lower bound for investment and for output. So one very easy way to prevent explosion of output is just to limit it artificially. Well, of course, he was a bit smarter than this. He didn't just say, let's limit it artificially. He tried to give economic meaning for these bounds. And you can think about it in the following way. Well, I think, yes, I will explain the bounds in the next slide. So the idea was the following. For Higgs now, the investment was still a sum of autonomous investment, but now, it's not a big difference actually. Now the induced investment, so investors do not respond to differential in consumption, they respond to differential in output. It's just a kind of a generalization of this idea that investors respond to a differential of economic activity. You can measure economic activity in terms of consumption or in terms of GDP, for instance. So here is GDP. So it's the gross or GNP if you don't have trade. So right, so this is how the investment looks like for Higgs. Consumption is still the same, still the same multiplier model. And then if you just do the exercise of expressing output as a difference equation, you get this. This is without the bounds. So there are no upper and lower bounds to the output. This thing can still explode or die down. All right? So this is what actually Higgs said. This is the private investment or the induced investment. Or rather, let's say, let's first look at the output. This is the output. he puts an upper bound to the output, which is called YC. C stands for ceiling, by the way. Right? So the output can never be bigger than the ceiling. Now, what could be an economic reasoning for introducing a ceiling on the economic activity? What do you think?
You have a fixed amount of capital in some period of time, so you cannot produce. You have some structural limitation in one period.
Yes, so yeah, basically that's the economic reasoning. There's only so much investment you can do. At some point, making new investments is not profitable, right? It's the so-called diseconomies of scale, right? You're limited, your resources are limited. Employment, employment is limited. Physically, the amount of people you can hire is limited. Natural raw materials are limited, so there is a limitation to production, which you hit at some point. In fact, this is one of the criticisms of this model, that yes, in principle, it is possible that we hit this kind of, as you said, structural limit to investment, but we're not sure if we can ever reach it in real life, right? Because the examples when people have not been able to invest because they couldn't hire more people physically, or because they couldn't get more raw materials, are not so many at all. So, but that's for later. For now, this is the ceiling. Now, his idea for a floor on investment is the following. So F stands for floor. You see, the induced investment, or the private investment, can never be lower than this floor, and this floor is negative. So the idea was the following. You have some kind of capital goods, a certain amount of capital goods. Let's say you have 10 factories, for instance. At each time period, they depreciate, as you all know. So there is depreciation. If you do not cover this depreciation, you're kind of, or let's say, yeah, so the idea was this. If you do not cover this depreciation at all, so you invest nothing, you're kind of, let's say this is the worst thing you can do. In the sense that if you don't cover your depreciation, and then in addition you sell some of your factories, this would be equivalent to actively destroying capital. This was Hicks' idea. And he didn't think that on the aggregate, people or capitalists actively destroy capital. So if the output goes down, if the differential in the output goes down, let's look at this. This is the accelerator. So if this is negative, which means that the output goes down, there is a recession, this tells you that you have to disinvest. Disinvest meaning negative private investment, so you kind of sell your capital goods on the market. But if you need to disinvest more than your depreciation, this would amount to actively destroying capital. And Hicks didn't think that this is what people do. On the aggregate, it may happen that individual people indeed not only let their machines depreciate, but they also sell them, disinvest them. But on the aggregate, he didn't think this is the case. So if you see a recession, if you're a capitalist, and you see a recession, the worst thing that you can do is to refrain from investment. So just sit, let your depreciation go. Let your depreciation go. So the worst disinvestment that you can do is your depreciation. Not worse, on the aggregate, that is. That's how Hicks reasoned for this floor of the investment. Is that clear? Because it kind of, at first sight, it looks counterintuitive. Why shouldn't I be allowed not only to not cover my depreciation costs, but also to sell everything I want? You are allowed to, but on the aggregate, Hicks argued that this doesn't happen. So people just, on the aggregate, they just let their things depreciate, even though, according to the accelerator model, they should have actually sold them as well. All right. So now, this is how the economy looks like for Hicks. This is the induced investment, and now you can immediately see what happens. I will just walk you through the business cycle creation. Let's say we have a boom, right? So economic activity rises, it rises, investment rises, consumption rises, everything is fine. At some point we hit this ceiling of output. So let's say for 2 periods, 2 consecutive periods, we hit the ceiling. What investors would see is no differential here. At some point they would see no differential because we hit the ceiling twice. This equation would tell them that their private investment has to be 0. So they invest basically nothing. They let things, they only cover their depreciation. That is the point. So 0 induced investment means addition to the capital goods, but they still cover their depreciation. So that is 0 if the new investment, induced investment is 0, the total investment in the economy would decrease. If the total investment of the economy decreases, the output in the next time period would also decrease, because the output is the sum of investment plus consumption. When the output decreases, then this difference in the next time period becomes negative. It's not 0 anymore, it's negative. So now, depending on the value of the accelerator, if is negative but not smaller than the depreciation, it means that capitalists, they still disinvest some of their capital goods, they sell them, but the amount they kind of disinvest is not larger than the depreciation. If at some point this thing, the amount they have to disinvest, becomes larger than their depreciation, they don't disinvest, they just simply don't cover their depreciation. So this is the depreciation of capital minus IF. So the investment, the induced investment, would be negative. So depreciation is not covered, but together with the autonomous investment, remember government is spending all the time, it makes the total investment 0, exactly 0. All right, and this is in fact the definition of the floor. The floor, when you hit the floor, the total investment is 0. In other words, this equals this in order for the total investment to be 0. So you've hit the floor, total investment becomes 0, and yeah, so this is the cycle. You have to implement this in Vensim, so you'll get a much better intuition how it works with the ceiling and the floor. By the way, this is a new kind of a self-study. So I still haven't done the Vensim models. There are 2 models that you have to develop. It's the Hicks model and one more that you'll see. So I still don't know if it's possible, but I assume it is. So let's see. All right, we'll continue after the break. And let me just remind you, please come and pick up the evaluation forms, course evaluation forms, in the break. Just put them on your desks, and we will evaluate the course after the break, actually. So you don't sacrifice the break. All right, guys, let's resume. Before we go into the course evaluation, I have a few announcements to make. One of them, oh, no. Yes, I was about to shut off the beamer instead of just doing this. One of them is an appeal from Group V member Laura. She's looking for her group members. So if group members could raise their hands, who is in Group V? So only you 2 guys for now. So you can sync later. All right. Now the 3rd online quiz. Remember, we have a 3rd online quiz. Some of you need to pass it. The 3rd online quiz will most likely go online on Saturday or Sunday. and you have 1 week maximum to do it, because I need to know who's going to get the testat and who's not going to get the testat in advance and communicate this to the department. So expect an email in the weekend, Sunday at the latest, yeah. With this, let's go to the course evaluation. This is the information you need to put in. This is the course number. I hope you can read it. These are zeros and not big O's. And the optional thing is this. And let's say we can spend about 15 minutes, 10, 15 minutes on this, on the evaluation. I mean, don't overthink it. Just be honest. Yes.
The course ID doesn't seem to fit in that. That's true, actually.
Really?
I think the L is for every course. So.
1 sec. Yes, so basically, let me see. It should fit. 351.
If you skip the hyphen, it fits.
No, 541.
There is no need to put the other. Exactly.
Well, this is what they gave me.
Yeah, but there is no need to put the other.
Okay. I trust you then. All right. So don't put the L. Does it fit now? Okay. Let me see if I'm obliged to say something else. Yeah, it's about me, it's not about the lecture. That's what I have to tell you. But you can still put your opinion about the lecture in the manual feedback. If you're finished, please bring the forms here. Or let's try to collect them in a more intelligent way. Just, I don't know, how should we do it? Pass them on? I just bring them here. Thank you. Time's up. No. Okay. Thank you. They're anonymous, as I forgot to mention. Thank you. Thank you. Thank you. Oh, okay. Thank you. Thanks. You guys are done?
Does it work? Because I already write.
Yeah. Yeah, it does. Thank you. Yeah. All right, so let's resume. Oh. Thank you. So I was describing the Higgs model. The economy in Higgs model is given by these 4 equations. Thank you. And the most notable thing to notice are the two bounds, the upper bound and the lower bound. The upper bound is on the output, and the lower bound is on the investment. Once again, let me reiterate, there is only so much output that we can produce physically, and there's only so much disinvestment that we can do without actively destroying capital, which Higgs argued rational investors do not do. They simply refrain from investment. Now, if you calculate the steady state, by the way, these are, as soon as you have max and min, you have piecewise linear functions. So this is not linear in this case, but you have piecewise functions. Don't concern yourselves with this. The point is that mathematically this model has not been fully analyzed yet. It's simply complicated. So papers come out all the time finding some exotic behavior of this model, which is more of a theoretical importance than any real practical consequences. Just as a side information. So if we express the output in the same way as we did before, in terms of the output in the previous 2 time steps, so we get the difference equations, you get the equation number 1. This is the yt. If you set yt equals to yt minus 1, to get the steady state or fixed point, you get the YFP, which is this. Right, so obviously if there is no government spending at all, meaning the autonomous investment is zero, then the steady state is zero. So this model cannot support basically any economy unless you have government spending. That's the fixed point. It can still have oscillations around the zero fixed point. That's a different issue. So the two bounds as I described them, the first one is the so-called full employment bound on the output. So as soon as we have full employment in the economy, we cannot produce more. This is as simple as that. Even though there is investment and there is consumption, increasing investment, we cannot keep producing more because we have basically diseconomies of scale, as mentioned here, labor force, raw materials, and so on. The lower bound is the so-called investment, lower bound on investment. What this means is explained here. When the output decreases too fast, which would indicate, according to the accelerator, that investment, or rather disinvestment, have to increase more than depreciation. In other words, not only will you not cover your depreciation, but you will also disinvest more. This would be equivalent to actively destroying capital on the aggregate, which Hicks argued does not happen. And people seem to agree with him. All right. The analysis of the Hicks model, we're not going to do any mathematical analysis, but just as a just to let you know that this has been done, and people have managed to prove. So this is a theorem. You don't need to understand it. What this says is basically it could be proven that there is a so-called closed set, or think about it as a space, or bounded region of space where this model, the dynamics of this model resides. All right. So any fluctuations that emerge are bound or bounded within a confined region of space, and this is called K. It's a closed curve. Anyway. Right, so you can prove what this means is there are no exploding oscillations. There is no exploding regime. Right? If there was an explosion, you wouldn't be able to bound the dynamics in any finite region of space. All right, so this is the proof, mathematical proof that now we don't have explosions. All right, so what are the consequences of this so-called theorem? As I mentioned, this proves that business cycles exist because the dynamics are confined. Right, so another good outcome of this model is that fluctuations can be either periodic or quasi-periodic, which is nice because we know that in real life business cycles are not perfectly periodic. And in the Samuelson model, we always got perfect periodicity. Now, I've simulated the model with R. These are not Venn graphs, but R graphs. You will have to produce Venn graphs like these. This is for the next week, right? Next Tuesday we have the Caldor model. Anyway, so what you can see is depending on the parameters, the multiplier alpha and the accelerator beta, you can get damped oscillations. So on the upper plot you have time versus the output, right? Okay, so if I wanted to be consistent, I would have put all these time graphs on top, but apparently I didn't want to be consistent. I don't know why. Anyway, so this is the time development of the output. You can see it's damped oscillations. The corresponding phase plot, which is just y at time t versus y at time t minus 1, is eventually reaching this attracting point. These are the so-called quasi-periodic or aperiodic cycles. So there is no clearly defined period of these cycles, but they're still bounded, which is nice. And by seeing this in the phase plot, these fluctuations, you can tell that they're aperiodic. It looks like this. They look periodic, but in fact, if you look carefully, they're not. And periodic cycles, depending on the parameters for this alpha and this beta. As you can probably guess, the next logical sequence in the lecture is to criticize this model, right? We introduced the Samuelson model, we criticized it, and we saw why the Higgs model needed to be developed, namely to address this explosion. Now we address some criticism for the Higgs model. Some of the criticism still remains from Samuelson, namely the alpha and beta, the multiplier and the accelerator, are constant, which is again not realistic. More importantly, however, people have managed to show that the existence of upper bound is not necessary to produce oscillations. Even if you disregard this point, then you can criticize it further by saying existence of upper bound is not even realistically provable. Right? We can never prove that this upper bound exists, and even if it does, we can never prove that we'll reach it, right? On the aggregate, that is. And why is that like a point of criticism? Well, people have observed that in none of the cycles in real life, up to 1980 when this model was developed, and even now, none of the business cycles were caused by hitting an upper bound. By full employment, for instance, people not being able to employ, capitalists not being able to employ more workers, or running out of raw material. So none of the business cycles have been caused by an upper bound, so we may never reach it, even if it exists. It's like this equilibrium concept. It may exist, but we may never reach it. And it's not even known whether we can reach it at all. Right. I had a short discussion in the break about investor behavior. And remember, here the reasoning was that as output goes down, so there is a recession, investors just refrain from investment. They just let depreciation work. What happens sometimes, well, often in real life, is exactly when there's a recession, people invest because the cost of investment is cheaper, and then they can, so basically they can increase their capital stock and be at an advantageous position when the boom comes. This is not what happens here because there is no anticipation included of investment behavior. So investors do not anticipate the ensuing boom after recession. That's a valid criticism, obviously. Most importantly, however, in all these models, even if you kind of decide to overlook all these points so far, cyclic behavior is generated exogenously. So we impose these parameters alpha and beta on the system. Who is to say what's the multiplier effect for consumers? Well, we just pick up a value, we see a business cycle, and that's it. But it's an exogenous effect, and we don't like this. We'd like to have an endogenous effect, and that's why the next model was introduced by Richard Goodwin. It's an endogenously generated business cycle. So a short introduction for this guy. The most important probably is the second point. He is one of the founders of endogenously modeling, endogenous models of business cycles. Let's get right into the model. So his model is a little bit different in the sense that to generate endogenous business cycles, you need to introduce more dynamics in the model, right? So far, in these models, we only had basically dynamics in consumption and in output. But now he said the following. Think of two social classes, capitalists and workers, like the Calder model. The workers get some wage, W. This is the real wage. That's important. It's not the nominal wage, it's the real wage, so adjusted to inflation. L is the number of people employed. So, I mean, it may be a bit confusing when it says employment, but it's the number of people employed. Then obviously, mu is the share of output that goes to cover costs of labor. So salaries, you may think, for all the employers, right? So W times L is simply the total salary of all the employers, of all the employees, divided by the output is the total share of output that goes to cover these costs. And L over N is the share, is the employment rate. Okay, so it's self-explanatory. Now, capitalists, two more assumption is that capitalists always invest everything they get. So the capitalists get some profit, they save everything, and by kind of assumption of classical economics, savings are used for investment. You know, they're not used to just have cash in the bank, but they're used for investment. So all the profits are reinvested back into the economy. This is what it means, propensity to save is 1. Basically, they always save everything, and in turn, everything is invested. By kind of extension, consumers consume everything. So the consumers consume entirely their income. And now if you write down a little bit the equations for savings and investments, so as I said, savings of capitalists is equal to their investment, so they invest all their savings. This investment goes to increase the capital stock, right? So K dot increases by the amount of investment. And here, if you remember the Solow model, we have not included depreciation of capital. In the original Goodwin model, he did not include depreciation. So all the investment goes to cover, to increase the capital stock. And then if you express, where is it? Right, so if you, right, so so basically the investment would be, the investment of capitalists would be their earnings minus the amount they pay to workers. And that would be the stuff that is left for investment. So that's what they invest. So basically this is an equation linking K dot with output and W and L. Further assumptions. These are a bit more economic assumptions now, and they would require a bit more explanation. Now, how many of you have heard of the Phillips curve? Quite a lot, yes. This is a standard relationship between unemployment and inflation. And this is a linear Phillips curve, right? Most of you know this kind of nonlinear, or rather like this nonlinear Phillips curve, but this is a linear Phillips curve. What does this mean? This is the increase, the relative increase, because we divide by W, of the wage, of the real wage, right? So in other words, the percentage increase of the real wage. This one here. And the reasoning goes as follows. At times of full employment, so this was the employment rate, remember? At times of full employment, workers have more bargaining power, right? Because they can argue, well, if you fire me, or if you don't increase my salary, I will leave, and you will have troubles hiring somebody else, because we have full employment already. So when the employment rate is high, the increase in real wages is also high, right? Because workers have more bargaining power. If we have a lot of unemployment, so basically the employment rate is very low, then workers' bargaining power decreases, right? There is a lot more substitute for these workers available out of the unemployed population. Therefore, when this thing decreases, the real wage also decreases. So if you look at this is a curve which basically goes like this. So on the x-axis you have the employment rate. On the y-axis you have the relative increase in real wage, and it goes like that. So when the employment rate increases, bargaining power of workers increase, and real wage also increases. So this is the assumption for the rate of change, the relative rate of change of the real wage. Typical assumption is that capital output ratio is constant. So basically, what does this mean, actually? Capital output ratio is constant. It means that at each time period, a fixed proportion of the output is always capital, right? So if the output increases, the capital goods, meaning machines, factories, and all this kind of stuff, also increase. All right? And you immediately see a deficiency in the model. There is no technological progress, no innovation. In real life, we know that due to innovations, the productivity of capital increase. So the productivity of a machine may increase and produce more output than before. But according to this, the only way to increase output is to buy another machine, because the productivity of the machine is fixed. There is no innovation. I just cannot refrain from, or kind of restrain from introducing criticism as I introduce the model, but we have a separate slide for the critical points. All right, labor productivity now, this is a more realistic assumption, grows at a constant rate. Okay, so this is the amount of people employed. This is the rate that labor productivity grows. It's alpha. Right, so for a fixed amount of people, if that is positive, the output would increase over time. Because over time, at each time period, the productivity of each single employee increases. As people become more specialized and more adept at doing their jobs, this assumption is somehow justified. And, well, yes, the population grows at a constant rate. And this is the rate n. It's kind of an exponential growth of population. I believe that's not so unrealistic, especially today. Probably, if you want to improve the model, you can introduce some kind of carrying capacity restraints, like in the rabbit and fox model. So you can introduce some S-curve, but for now, let's keep it simple. These are the basic dynamics. So let me ask you, in your opinion, what are the control parameters in this model? What are good candidates for the control parameters? Let me remind you, this is the complete model. So we have mu is the wage share, V is the employment rate, and then we have all these other things here. Sigma, alpha, and n. Because what we want to do is now to define a dynamical system which relates our control parameters. And remember, control parameters are those that can be changed relatively easily. Well, yes, relatively easily, by policy, for instance. It's not actually so easy, or let's say so intuitive this time. Turns out good candidates for control parameters are the wage share of output, so mu, this one, which means how much of your output goes to cover the labor costs. In other words, you can change W, the salaries. And V, this is the employment rate. These are things that change most often. So what we want to do now is to have two equations, two dynamical equations, coupled differential equations, relating mu and v. This is what we want. Now, I'll show you how to get a dynamical equation, a differential equation, relating mu dot, so the rate of change of mu, and v, the employment rate. In exactly the same way as an exercise, if you'd like. It will not be asked on the exam. You can derive the second differential equation relating v dot to mu. The only thing you need to know is the chain rule for differentiation. That's all you need to know. This is the whole exercise. Well, let's see. Mu was defined as this. So if you want an expression for mu dot, you simply have to differentiate that thing. You have to differentiate this thing. Well, what is the, with respect to time, okay? What is the derivative of this? It's the, so think of this as W times L over Y. Well, let's look. It's the derivative of W times L over Y plus W times the derivative of L over Y. It's the chain rule, right? So, by the way, this dot refers to the derivative of this ratio here, not just to the derivative of L divided by Y. So if you don't want to be confused, maybe you can put a bar here, or you can put a prime here, like I've put it here. Anyway, then we continue expressing it. This remains the same. The derivative of this whole fraction, L over Y, remember L over Y was defined, or rather Y over L was defined as the growth of labor productivity. It was e to the power of alpha times t in the previous slide. Well, L over Y then would be just 1 over e to the power of alpha t, or e minus to the power of minus alpha t. Derivative of this, well, that's easy. Derivative of an exponential is simply the exponential itself times the derivative of this thing, which is minus alpha. Therefore, we get W alpha e remains minus. This thing still remains the same. This is the same. Now, e to the this exponent is simply L over Y. L over Y. We can factor L over Y. So we can factor it out in front of brackets and rewrite this expression like this. Okay? So if you multiply the brackets out, you would get exactly the left-hand side. What is that, though? Well, this was defined as the rate of change of the relative wage, which was simply the linear Phillips curve, this one. Minus alpha times this is mu. It's the amount you pay to all your employees divided by the output, so the share of output that goes to cover your labor costs. So it's mu. Therefore, we get a differential equation relating mu dot and obviously mu, but also v. Obviously, in the same way you can go with the v. I will not do it now to save time. But it looks like the one shown. So basically our system now is these two coupled differential equations. And you know how to analyze it. First we try to find the fixed points, and then we try to find to investigate the stability of these fixed points. We already did this in lecture 10, I believe, where we were looking at Jacobians and stuff like that. So one obvious fixed point, so just set these two derivatives to 0. One obvious fixed point is 0, 0, right? If mu is 0 and v is 0, everything is fine. The derivatives are 0. This is a trivial fixed point, so we're not so interested in it. Another fixed point would be obviously when the expression in the brackets are 0, this one and this one, right? So when this is 0 only when v is equal to alpha plus gamma divided by rho, this one. In the same way, this is 0 only when mu is equal to this. So this is another fixed point. And now we can calculate the Jacobian of our system, introduced in lecture 10. So the Jacobian in general, is given by this. What does it mean in general? So not evaluated at a fixed point, but just taking the differential. So remember, this is du. So we differentiate this thing with respect to mu, and we get the upper left entry in the Jacobian. This thing with respect to v differentiated. This thing with respect to v differentiated, we get the upper right entry, and so on. If we evaluate the Jacobian at the non-trivial fixed point, so not the 0, 0, but the other one that we found, the Jacobian equals to this. By the way, I'm sure there are no typos here because I just did it manually, without trusting that people who did it 2 years ago did it right. So this is the Jacobian at the non-trivial fixed point. We do this, why? To analyze the stability of the fixed point. Turns out that the trace is 0. The trace is simply the sum of these two diagonal elements. It's 0. The determinant is positive. It can be shown. If you calculate it, the determinant is positive. And now if you go back to lecture 10 and look at the illustration which relates the determinant, the trace, and the types of fixed points, then you can see that given these conditions, the fixed point is a center. Okay, what does a center mean? You'll see, I believe, on the next plot. Oh, yeah, minutes. Yeah, they're always building something. All right. This is what a center means. Now, this is our fixed point. Our fixed point is here. If we just disturb it a little bit, randomly, we get orbits, increasing orbits. Well, it's kind of difficult to be very precise with this, but imagine kind of a spiral, increasing spiral, which eventually settles down to this center, or this circle, this one. Okay? Now, if we're at this center and we disturb it a little bit, and just by chance we disturb it in a way that now the dynamics is here, a bit up, then again an increasing spiral would go to the second circle, and so on. So starting from a fixed point, we end up in one of these circles, one of these many infinite number of circles depending on the shock. And obviously depending on initial conditions. Right? If the initial condition is here, if we start with the initial condition here, obviously we're going to converge to that circle. So that's what the center means. And this is nothing else but a business cycle, right? Look, mu on the v-axis we have, well, on the x-axis we have mu, on the y-axis we have v. So what happens is the share of output which goes to employment and the employment rate fluctuate. That's another way to quantify a business cycle. Instead of looking at output, how output oscillates, you can just look at employment rate and salaries. Right? So when employment rate increases, look at it here. When the employment, well, let's look at this circle. The salaries increase here. Employment rate also increases. That's this assumption that when employment rate increases, bargaining power of workers also increase. Therefore, their salaries would increase as well. Right? So, employment rate increases, bargaining power increases, salaries increase too. So share of output that goes to salaries increase. At some point, however, the opposite happens. The salaries decrease, whereas the employment rate increases. So that's kind of a predator-prey dynamics. that we saw with the rabbits and foxes. Well, it's not exactly predator-prey, it's like predator-prey. So these are the business cycles. And again, some criticism. It turns out that if you introduce just small fluctuations in the model, very small, but which are nevertheless economically meaningful. And for instance, I've given an example. If the capitalist's propensity to save is not 1, so it's not the fact that everything they get, they save it and invest it, but if it's a decreasing function of the wage share, meaning the more they have to pay to workers, the less they would save. For instance, they would keep some money in the bank. Let's put it this way. They would not invest everything they get. Then the fixed point becomes asymptotically stable, and there are no business cycles anymore. Right? So this is kind of a little disturbance in the assumptions of the model, which completely changes its behavior. That's one criticism. Second criticism is people have shown empirically that it is possible that this happens. So labor productivity and the sum of the labor, well, the increase of labor productivity and population to be negative. If that is true, we get this. Then the fixed point, this is the fixed share of output that goes to salaries, becomes larger than 1, which makes no sense economically. Right? You cannot pay more salaries that you have money available. So that makes no sense. The same thing can be shown, it happens with V. So this model is not stable in a sense. 2 empirical data, that's the most impressive thing. Or let's say the worst thing. All right, we're almost at the end. Well, I still have 1 minute, so let's keep this this clock. I just want to mention a few general assumptions about the multiplier accelerated theory. You know, all the models so far except the last one had multiplier and accelerator in it. And I've tried to summarize kind of the most important ones. First of all, both accelerator and multiplier assume that investment or supply is very elastic. So if you want to ramp up production or ramp down production in response to supply or output differential, you can do this immediately, which is obviously not realistic. Furthermore, the accelerator assumes underemployment. Why? Because if you need to increase production rapidly, you need to be able to hire people at ease. So there must be some unemployed people just waiting for you to hire them if you want to increase production. Right? If there are no unemployed people available, you won't be able to increase production. Yet, the accelerator concept by itself requires this in order for it to work. Another thing is there must be no unused capacity. So all capacity must be utilized at all times. Why is that? Well, if there is unused capacity, let's say 5 of your factories are not working, when you see a differential in consumption or a differential in output, you will not make new investments to build new capacity. You will just reuse, or you will just use some of this unused capacity. So there would be no new investments, yet you will be able to produce more. And this is only possible if there is unused capacity. Therefore, the accelerator concept assumes all capacity is utilized at all points of time, which is again not perfectly realistic. I mentioned it already. Both of these concepts completely neglect expectations. We had very simple backward-looking consumers. They only cared about their last salaries, and we had very limited investors who only cared about the differential in the last two periods. There is no forward-looking in any way. Both accelerator and multiplier are constants. Yes. Yes, so these are the most important assumptions of the multiplier accelerator theory, and depending on your personal preferences, you may or may not relax them. So disregard them, in other words. Or you might just completely disregard all these theories by saying they're completely economically not realistic. But it's basically personal taste, I would say. This is the last self-study. You have to implement the Higgs and the Goodwin models in Vensim. As I mentioned, this is a new self-study. I myself haven't done it yet. I assume it's possible. It doesn't look difficult. So let's hope I'm right. Thank you, and I'll see you next. By the way, something important, sorry. For next week is the Q&A session. Please come with your questions and try to just ask me like lecture 10, slide 19, this graph I don't understand. Let's try to keep it short and concise so that there can be as many questions as possible. All right, see you next week. Basically, this is the same slide as last lecture. A quick reminder, what we looked at so far was kind of a mathematical way to get oscillations, right? We looked at basically the nonlinear dynamics. We have a dynamical system. We didn't specify exactly what dynamical system that is. Could be everything. We looked at factory, supply chain, for instance, and then we simply took control parameters and we saw how the dynamics of the system changes qualitatively in terms of bifurcations by varying the control parameters. But there was still kind of something left out, and that was more of a real application of these concepts in terms of economics. So that's basically the last two lectures, the last three lectures actually, looking at oscillations, looking at the economy as a dynamical system. And this is not something new. Economists have been trying to do this precisely to address criticism for the equilibrium assumption that neoclassical economics has, and that is economy is always in equilibrium, and all we can study actually is how the equilibrium changes if we change some fundamentals, right? Obviously, this is not a satisfactory explanation of the real world, and that's why people started modeling business cycles. But I have to say that the economists who try to model business cycles, most of them, I would not like to say all of them because I'm not an economist, so I don't know. I don't have all the information, but most of the economists are not neoclassical economists, right? So you will not find proponents of free markets, of efficient market hypothesis. You will not find an economist like Eugene Fama, for instance, studying business cycles, right? Because for neoclassical economics, there is no problem. If we're in a recession, for instance, there is not enough supply. So good morning. I have one good news for you, and that is that this is the last lecture in the course. We've made it. It was easy, right? I mean, probably the most difficult thing was waking up early in the morning, as evident by the influx of people. I hope that a lot more of you show up after the break so that we can have the course evaluation. The forms are over there. Well, let me fix the resolution again. Oh, and now I understand what the problem was. Oh, God. Just doesn't want to. Keep it. Okay. Finally. So the forms over there, we'll do it after the break. I ask you to take them during the break, so take them at your desks during the break, and the first 15 minutes of the second part will be spent on the course evaluations. I am obliged to say that the course evaluations are not so much about the lecture itself, but more about the lecturer. So most of the questions will be evaluating the lecturer. So if you think that the course, if you have an opinion about the course material, that is, the course is boring or not interesting or it could be improved and so on, you can write this down in the manual feedback section. But don't expect that you get questions evaluating the course concept. This is evaluated in a different way. All right. So today's lecture continues kind of what we started last time, and that is the business cycles, modeling business cycles at each time step. Investors, they invest a fraction of the increase of consumption, right? So if consumption increases by, let's say, 1,000 arbitrary units, the increase, or the differential in consumption, then investors would invest a fraction of this, not a fraction, but a multiple of this. It could be larger than 1, and this is called the accelerator. We'll see this in details. So the second model is, just to give you an idea, the assumption here is that the economy grows trend-like, so there's a trend-like growth, but oscillation, you don't see this trend in the short term. You only see oscillations around the trend. So the economy grows basically like this. John Hicks, it's an improvement of Samuelson model. We'll see what improvement exactly, and then when you look back in this slide in retrospect, you will understand what this means. And the Goodwin model is different from all these other models because it explains business cycles endogenously. Probably you're all familiar with exogenous versus endogenous. Only with the Goodwin model we can get business cycles that are produced by the internal dynamics of the system, not imposed by some external parameter. We're going to see this. So Paul Samuelson, I tried to, by the way, I forgot to say, this is a brand new lecture. So it was never given in the years before. These are kind of infant slides. And yesterday I was going through them again, and I found a lot of typos. So depending on when you downloaded the slides and printed them out, you may have a slightly different version. So to be safe, just download them again. They would be the correct ones. If you've downloaded them in the morning and printed them out just now, then you're fine. All right. I tried to give you a little bit of information about each economist. So for instance, Paul Samuelson was already at university at the age of 16. You can read this, enough demand for labor. Then what will happen is the wages will go down, and eventually it will become profitable for employers to hire again. And then the economy will bounce back. So there is no problem for neoclassical economists to explain recessions and business cycles. But it's still not satisfactory. So all these economists, starting actually quite a long time ago, 1938, they've been trying to kind of depart from this classical view. And that's why we emphasize here. This is not an economics course, but I just like to give you some kind of economics foundation for doing this. It's not just because we like to have some mathematical equation and call this variable supply and this variable demand. Last lecture, I introduced the Caldor trade cycle. It's one of the most famous business cycle models. I saved the economics behind it. It's written nicely in Caldor's paper. Now I'm thinking that it may be a good idea to introduce the economics. So I will probably, introduce it briefly. So I will probably do it next week at the summary lecture. I will introduce this quickly these nonlinear functions, investments and savings functions, and explaining kind of the economic rationale behind the slopes and the shapes. Basically, it would be a summary of the Cowdor's paper. It won't be new to you if you've read the paper. Today, we continue with more business cycle models. And these are the models, with the exception of, now I cannot use this tool, so let me try to open the lecture in another way. Okay. Now I can do this. Right. These are the models we're going to be studying about. We're going to be talking about, with the exception of the second one. It's just we don't have enough time. So all the others we're going to address, with the exception of the second one. So the first one, how many of you have heard the name Keynes, the economist? The economist. Oh, wow, nice. So you probably know his his economic idea, which is not as what popular opinion holds, that he's a socialist or communist. He's actually trying to fix capitalism. So his main concept is that through fiscal politics, so government spending, public spending, you can fight recessions, right? So if there is a recession and there is not enough private investment, so firms don't want to invest, don't want to hire, then it's the government who can step in. And I always think about all the construction work going around Zurich all the time. Although to me they sound like perfectly, they seem like perfectly good streets, but they're still being reconstructed. So it could be, and probably it is, some kind of Keynes concept there. But this is his main idea. The government, through fiscal politics, can fight recession. Obviously, this is at odds with the standard markets are most efficient, all this kind of stuff. Well, Keynes was criticized a lot, especially by Milton Friedman. He's another famous economist, proponent of the efficient market hypothesis and so on, but that's irrelevant. The point is that all these models, if you want to model business cycles, you kind of assume Keynes' position. So all these models are just mathematical representations in one way or another of his ideas, because actually he didn't leave any formal mathematical description of his ideas. So people are trying to formalize them. Of course, adding a little bit here and a little bit there. The first one is Samuelson. It's a very interesting model, very simple, in fact. That's why it's interesting. So he simply assumes that consumers always consume a fraction of their income. This is called the multiplier concept. So you multiply kind of the income by a fraction, and this is what you consume.